Okay, guys, welcome back. This is lesson number three. Lesson number three is a review for our units. We are completely done with unit number 8 as of today. This is an assignment that is due at the end of today at 11:59. So homework number 1 should be is due today at 11:59. Most of you have completed it. I've opened it up again in case some people need some extra time. So if you've already done it, don't go back and change anything. Just leave it alone. I'm just reopening it. Um, Lesson number 3, the review for the unit 8. I put a Google form with a couple of questions that I want you to do. Then go on to Test Wizard. There's a couple of questions there as well. No, I'm not. Now I am. All right. There's a couple of questions on Test Wizard there as well. I want you to do the reviews before you get to the quiz, all right? Do the review before you get on the quiz so you have enough practice and you can get a good grade on the review. All right. So, properties of acids and bases. Properties of acids, they are sour, corrosive. They have a pH level lower than 7 and they form hydrogen ions when placed in a water based solution or when placed in a regular solution as well. Those hydrogen ions, it could be hydrogen ions, which is an H plus ion, or hydronium, which is a H3O plus ion as well. So hydrogen and hydronium are both used interchangeably when we're talking about acids. Then they also turn litmus paper red. They turn methylene orange into red, and they also turn phenylalanine colorless. When we have bases, bases have a pH level higher than 7. They are slippery. They form hydroxide ions, hydroxide, which is a OH minus ion. When they're in solution, um, bases are caustic, so they're very harmful to the human skin. They taste bitter. Remember when we tasted the tea in the classroom? Yeah, that's a base. And then they turn red litmus paper blue, and they turn phenylalanine color pink. All right. So what is electrolyte? The reason why we're bringing electrolytes in because it's always good to reference, and electrolytes really do have to do with acids and bases as well as salts. So electrolyte is a substance that produces electrically conducting solution when dissolved in a polar solvent such as water. Let me give you the simpler term. A solution that produces electricity due to the breakdown of ions and the ability for them to flow or move freely. So anytime we're talking about a substance being able to conduct electricity, it's because it has free flowing ions. Must be able to remember that. The reason why we are able to conduct electricity is because we have free flowing ions, and if not ions, electrons. So, what are a couple of examples of electrolytes? Those are salts, acids, and bases. So you can find the acids on table K, you can find the bases on table L, and then for the salts, look on table F to see which salts are soluble and insoluble in some aqueous solutions. All right, so we have two acid-base theories. We mostly go with Arrhenius acids and bases, but the other theory is known as Brownstein-Lauer. Let's talk about Arrhenius for a moment, and then we go to Brownstein-Lauer. So Arrhenius acid bases, most common, they give a hydrogen plus ion, and the base gives an OH, a hydroxide ion. So hydrogen for Arrhenius acids and bases, it's really easy for us to identify them because they start with a hydrogen. And for Arrhenius bases, they also end with an OH, so they end with a hydroxide. That's an easy way to recognize Arrhenius acids and bases. When it comes to Brownstein-Lauer acids and bases, the acid is the donor while the base is the acceptor. So the acid is the donor and the base is the acceptor. If that's a little bit confusing for you to understand, this definition is a little bit better. So the more hydrogens it has, it's a base. The less hydrogen it has, it's an acid. So when it comes to Brownstein-Lauer theory, the more hydrogen it has, it's your base. The less hydrogen it has, it's your acid. Now, for Brownstein-Lauer theory, it might be also known as the alternative theory or the other acid-base theory. We mostly go with Arrhenius acids and bases. So when we're calculating pH, when we're calculating pH, what we do is, remember, pH is based on logs, and logs is based off the number of 10. So to calculate the pH, what you're going to need is the concentration of your acid and your base, and this formula. So for pH for acid is negative log and the concentration of that acid. And then for base, it's negative log the concentration of that base. But remember, base, the most basic is 14. So we subtract our answer from 14. So let's go through a couple of practice problems for acid and then base. Practice problem for acid is, what is the pH of a 0.0001 molarity aqueous solution of HCl? So I know I'm working with acid because I have HCl. My H is in front. So I'm working with the acid. That means I'm using negative log and the concentration of the acid. My concentration, once again, is a form of molarity, which I have capital M right here. So I'm going to write my formula. I always like writing my formula first. Then I'm going to plug the concentration where it says H3O+, that's hydronium. I'm going to plug the concentration in for where I see that. And this is what my setup looks like. And then I'm going to put it in my calculator the same way I see it. So negative log, parentheses, 0.0001. And I'm going to close the parentheses, and my answer should give me 4. For the base, this is our example problem. What is the pH of a 0.001 molarity KOH solution? I know that I'm working for KOH because OH is the indicator that I'm working with the base. So I'm going to go ahead and write my formula right here. POH equals 14 minus negative log concentration of my base. I'm going to put the concentration of my base where I see the OH minus. That's 0.01. And then I'm going to go ahead and solve for my negative log of 0.01, which gives me 2. So now my formula setup looks like this. 14 minus 2. And 14 minus 2 gives me 12. So that's the pH of my base. Now, a couple of pH practice, and this is the shortcut on how to do this. Based on the place value of the exponent of the concentration, the pH can be determined as long as we are dealing with 1. If we're dealing with 1 as the base number, meaning if we're still dealing with the number of the base number of 1 or 10, we can go ahead and find the pH value as well as the concentration. So, example, determine the pH of HCl solution if the concentration is 0.001. Now, if you can see over here, my concentration is a base of 1, right? There's no other number but 1 as my main digit. So, or my significant figure. So, with that being said, I'm going to count the place values after the decimal, and that's going to tell me what my pH is going to be. Because as long as we're dealing with a base of 10 or a base of 1, we're going to be able to find the pH. So, because this has 3 decimal places after, 3 place values after the 1 and the hundredths place value, the concentration is 0.001, 3 place values, so my pH would be 3. So over here, determine the pH of KOH solution if the concentration is 1.0 times 10 to the 12. Molarity, I'm going to look, because the 1.0 times 10 is also a base of 10 itself. I'm just going to look at the exponent to tell me what my pH would be, and my pH would be 12 because 1.0 times 10 is literally just 10, which is a base of, obviously, 10. Alright, so base of 10, and what I mean by that. When the pH value changes from 2 to 3, it changes based on the unit of 10, not 1. Once again, we're dealing with logs, so we're always going to be moving base of 10. When it comes to this part, I would say use a number line so you understand where we're going. So when we move from 2 to 3, we're moving based on a unit of 10, not 1. So everything is a multiplication of 10 or tenfold. Be aware if they want more hydronium or hydroxide. If they want more hydronium, you're moving lower down the pH scale. If they want more hydroxide, you're moving higher up the pH scale. So when the pH of an aqueous solution is changed from 1 to 2, the concentration of hydronium ion in the solution is, well, we're changing from 1 to 2. So my hydronium ion, I'm becoming less acidic, so I'm decreasing. And because I've only changed one value, I'm actually changing a value of 10, not 1. So I've decreased by 10. Another one over here. What is the pH of a solution that has hydronium ion concentration 100 times greater than a solution with a pH of 2? Well, if I break this down, hydronium ion is talking about the acidic side of my pH scale. And then I also moved 100 times greater. 100 times greater, well, 100 divided by 10 is 10. So that means I changed twice. I moved 2 times, right? So what is 2 times greater than a pH of 4? Well, 2 times greater than a pH of 4, automatically you would say it's 6. However, they want more hydronium. So instead of us moving up the pH scale, we're going to move down the pH scale. We're going to be more acidic. So instead of the answer being 4, the answer would be a pH of 2. Indicators. Indicators are organic substances that change color in the presence of acids and bases. So these might be a little bit off. Just check your chemistry reference table, like table M, for the exact amounts. So indicators, we have litmus, pH range 5 to 8, methylene orange 31 to 44, and then phenylalanine 8.3 to 10. So indicators work this way. If I'm using, let's say, litmus, which changes from red to blue, anything lower than 5 would be blue. Sorry, would be red. So anything lower than 5 would be red. And then anything higher than 8 would be blue. Between the range of 5 to 8 is where I'm having my color change. So if my pH scale, if my pH falls between that range where I'm having that color change, I wouldn't want that. So I want to find a pH indicator that's going to give me an exact color, not a mismatch of colors. So over here, which is the color of the indicator Thymo blue in a solution that has a pH of 11? Thymo blue is yellow to blue, and the pH range for that, for Thymo blue, let me just get that up real quickly for you. The Thymo blue is yellow to blue, and 8.0 we are yellow, and 9.6 we are blue. Because 11 is higher than 9.6, it would be a blue color. I'm gonna leave that there. Give you the answer right here. Alright, neutralization reaction. Neutralization reactions occur when an acid-base reacts with base react. The product of the neutralization reaction is a salt and water. We went over this. You can go ahead and look at that video to help you out with this. But remember, neutralization reactions are basically double replacement reactions. So we have my acid plus my base, which is going to form water, and then my salt. We have my acid plus my base, which is going to form water, and then a salt. All right. And then we have titrations, which is what we went over yesterday. So, titration is a neutralization reaction that is used to determine the concentration of an unknown substance. Remember, titration is a laboratory procedure that follows a mathematical process. So, we have a formula for that, which is down here. Once we find the volume of the unknown, we can take the volume of the unknown and multiply it by the concentration of our known and the volume of our known. So, M1V1 equals M2V2. I was just saying to the class the other day that molarity times volume gives you moles. So your moles of your acid will equal the moles of your base, or your moles of your known will equal the moles of your unknown. So this is just working with moles. All right, we have this question here. What is the molarity of a solution of LiOH if 15 milliliters of solution is required to neutralize 20 milliliters of 2 molar HCl? Gonna work through the problem right here. And this is what our answer would be. Now remember, this, I've already created a video on this. This is just a review. So if you have any questions, you can go ahead and look at that video to help you out. Now, for neutralization and titrations, there is a video already created for those to help you out. This is just to go over the previous material. So go ahead, work on your practice problems, and get ready for your quiz, and I will see you next time.